Hello! So, in this video we're going to be proving the Riemann indefinite integral theorem, or indefinite Riemann integral theorem. So, again, as usual, we have our f from that closed interval a, b to r. We're assuming that it's Riemann integrable, and furthermore we're defining this capital F thing on the same domain and range. And we're defining it to be f of x is the integral a to x, so that's where the independent variable is going, of f of t dt. So assuming we've defined these things, we want to know some stuff about capital F. So part A is saying that f is not just continuous, but actually uniformly continuous on that closed interval. And part B is claiming that if you have the little f, right, the beginning f here, is continuous at some point, then capital F is differentiable at that point. And in fact, that f prime of c is little f of c. So you may actually recognize that part B as being a piece or being very similar to what is often taught as the second fundamental theorem of calculus. And indeed, if little f is continuous everywhere in AB, then you have exactly the second fundamental theorem of calculus you tend to learn in, say, Calc 2 or Calc 1. All right, so these proofs aren't necessarily overly complicated. They are a little computational, and they involve sort of a little bit of cleverness, but they can be a little long, so I'm probably going to be doing some editing magic at some point in here. So start with proof of part A, and we'll see how it goes. All right, so part A. So since we are assuming that f is Riemann integrable from A to B, we have sort of specifically that f is bounded, i.e. there's some m, so I'll do the symbol. There exists m, a real number. It's probably positive, but I don't care. It's some real number such that, in fact, it would have to be positive, or at least not negative, such that f of x in absolute value is less than m for every x in AB. Okay, so that's just means to be bounded. You do the absolute value, so you have it bounded above and below. Okay, so let epsilon greater than 0 be given. And just to be clear, what we want to show, so WTS, we want to show that this thing is uniformly bounded. So what that means is there exists delta greater than 0, so that for any, let's say, x and w in AB, if the distance between x and w is suitably small, less than delta, then the distance between the functions, so we want to show that capital F is, so capital F of x minus capital F of w is less than epsilon. All right, so put this in parentheses. This is our goal. We're given an epsilon, so that's that epsilon. We want to show that there is some number, some delta I can choose, so that this is true. And in case it's been a little while since you've done this, it's really important that I've chosen the delta before I've chosen the x and w. That's what makes it uniform continuity. If I did it the other way around, if I said, okay, fix some x and w, then find a delta that works for those x and w, that's continuity, not uniform continuity. So the uniform means I have to pick a delta without it depending on the x and w, and then somehow it should work. Okay? All right, so I'll maybe do a little dotted line here. So we have that it's bounded by m. We've let epsilon be given, so I'm going to set delta to be something less than epsilon over capital M. And again, it may not be obvious why this works yet, but it should become obvious why it works once I've done it, right? So with a lot of these proofs, when you are writing them, the best way to go about it is to say like, let delta be blank, go through the rest of it until you get to a point where you need to substitute out delta in some way that, makes everything work, and that'll tell you what it needs to be, okay? So I'm gonna make delta less than epsilon over m. So now what do? Well, now I'm just gonna run through it and see what happens. So I wanna do this piece here, right? So I'm gonna look at f of x minus f of w. Okay, what is that? Well, f is this thing, right? So this is integral a to x of f of t dt, that's that one, minus the integral a to w now of f of t dt. What is that? Well, according to one of our theorems earlier, you can write this as, so I'll keep this, a to x f of t dt. But here I can flip those bounds and flip the sign, right? So I can make this plus integral w to a now of f of t dt. But this is now a middle point, right? So that is, according to yet another theorem of ours, and these absolute values are important, so I'm keeping them along. So this is just a middle point. I can cut out the middleman. This is going to be w to x of f of t dt. Okay. All right, now what? So now, according to one of our suggested problems, which I don't know if I've given you yet, but I will give you, this thing, if I take the absolute value of the resulting integral, which you can think of this for just the sake of sort of motivating what I'm about to do, this is some area under a curve, but in this it's signed area, right? If I ignore the absolute value, this is a signed area, so some positive and some negative might be fighting each other. If I instead replace it, I'm going to put something here, but if I instead replace it with taking the absolute value of f of t dt, then I'm only taking the positive version of area, so they're not canceling each other out, so I've only made things bigger, right? So if I take the absolute value and sort of crash into the integration, right? If I bring it inside the integration, I'm only making the result bigger. So again, this is just a problem. It might even make it a homework problem for you guys or an exam problem, but so I'm not going to prove that because that'll be something you guys will do. Nonetheless, sorry, forgot the w to x. But now I have absolute value of f, and as we noted, it's bounded. M is bigger than that, so I can make this even bigger. I should have made this. I could pick a yet bigger m and it would be strict, but I don't need it to be strict. So I can make this even bigger. Place w to x with now just m dt. Right? If I make the inside yet bigger, I only make the overall integral bigger. And now I have a constant integrated over this interval range. So this is just equal to let me do this. The distance between x and w times m. Now, as a comment, x and w are both dummy variables, which is actually important, right? Because the whole point is I had to choose delta before I chose the x and w, right? So set that, and I was going to write it down here, but I'll also note let x and w in AB, AB such that x minus w less than delta, right? If I didn't put this here, this is true for any x and w, just ever, right? So I was going to mention it down here, but it's sort of nicer to write it up there. Point being that delta is bigger than x minus w. So I could replace this with the bigger thing, right? This is less than delta m. And this is where you look at that and go, wow, I need delta. I need this whole thing to be epsilon, so I need delta to be epsilon over m to cancel the m, which is exactly what we did. So this is then less than, right? So if I replace delta with what it is, epsilon over m times m, which is just epsilon. So that gets me that the difference is less than epsilon for any x and w in here that are closer than delta. All right, and importantly, I've picked delta without depending on x and w. Okay. So this shows me, so I guess I'll write it, but thus f is uniformly continuous, right? It's continuous, but it's even stronger than that. It's uniformly continuous on AB. Okay. All right. So I have some room to start B. We'll see how it goes. Okay. So I want to make sure that there's nothing else I wanted to mention here. I should also mention, just as sort of a footnote, because I want to juxtapose it to something I'm going to do over here. X and W are both dummy variables. So I could have chosen X to be the bigger one and done it sort of a little nicer down here. But it didn't matter. Like, I could do this, I guess I could do that, which would be also true. Because if W were the bigger one, this would be a negative number, which means if replacing it with a positive would make it bigger. Either way, it would still be less than delta, so it wouldn't matter whether it was positive or negative. It just would be kind of goofy. So here, though, the fact that X and W are both dummy variables means I could choose the bigger one. The one I'm about to do, I don't have that luxury, and so I have to be a little more careful. So I'm going to do the other one. I'm going to try to juxtapose it to that choice where I could just sort of hand wave away the fact that I'm taking an absolute value there but not there, because it would still work. So proof for part B. So if f is continuous at C, then f is differentiable at C, and indeed f prime of C is f of C. Okay, so if we have that it's continuous, what does that mean? So first suppose f is continuous at C, and let epsilon greater than 0 be given. Standard, right? So what we want to show then is that we want to show that f is differentiable at that point, right? So we want to show, so maybe I'll do the first part first. So f is continuous, what does that mean? So let fix, let's say, delta equal to epsilon. So there exists this delta, specifically epsilon, such that thus for, let's say, x in AB, if x minus c is less than delta, then we have that f of x minus f of c is less than epsilon. This is what it means to be continuous, right? What we want to show is that capital F is differentiable, plus this thing, but we'll get to that in a second. So what we want to show is that f is differentiable. So we want that f of x minus f of c over x minus c. So we want that this thing makes sense, right? The limit as x goes to c. And moreover, we want that it equals f of c, So in particular, right, in the limiting sense, we want to show that this thing is less than epsilon, right? So again, this is a parenthetical, meaning this is what I want to have happen. I want to show that I can do this minus that and get something less than epsilon for when x and c are within delta. And I've claimed that delta equals epsilon is the delta that will do this, okay? All right, so like before, we're basically going to start by writing what this thing is. So here, let's start with this. So let's look at f of x minus f of c over x minus c minus little f of c. This is, in particular, 1 over x minus c times f of x minus f of c. So that's just pulling that out so it's a little easier to read, minus f of c. So what are these? Well, still have that thing, 1 over x minus c times. So f of x, that's this thing. So I'm going to do something here. So this is a to x of f of t dt minus the integral a to c f of t dt, and then minus this f of c. So here I'm going to do the same trick I did over here, right? So I could flip the bounds, make it a plus sign, kill off the middleman, and just go here, right? So if I have a to x, w to a, it becomes w to x. So here I have a to x, a to c, right? So it's going to become c to x. So this is 1 over x minus c times integral c to x of f of t dt minus. So now there's a really sort of nice standard trick you can use that is used a lot in this kind of theory, which is that we have a constant here, but it'd be sort of nice to be able to write this constant, this f of c, as an integral. And you can do that by sort of offsetting the result, because remember, if I took an integral of a constant, it's the distance of that interval times that constant. So if I wrote something like, and I'm going to put something here, if I wrote something like c to x of f of c dt, f of c is a constant, right? Because my variable of integration is t, and this is just some number. So the result is going to be that number times the length of the interval. But I want just that number, so I'm going to have to divide out by the length of the interval, meaning I'm going to have 1 over x minus c out here. And conveniently enough, by some purely happenstance, I'm sure, miracle, I have the same number in front, right? So this equals, so I can pull out the multiple, and in fact I'm going to pull it sort of all the way out. So I'm going to have absolute value of 1 over x minus c times the absolute value, and now I'm going to have the integral c to x. So I'm going to have f of t, these things got pulled out, so I'm going to have f of t minus f of c. Okay. All right. So now what? Well, I'm going to use the same sort of trick I did before, but I'm going to be even more careful than I was before. So this is less than or equal to absolute value 1 over x minus c times. I'm going to leave the absolute value on the outside, but I'm also going to have an absolute value inside. Right? So this is doing the same thing I did here, except I'm moreover putting an absolute value on the very outside on top of that. So that's an absolute value side. Okay. All right. So as long as my x minus c is less than delta, then I know that my f of x minus f of c is less than epsilon, right? So I've chosen that these things are less than delta. So that means that this inside here is less than epsilon. So I still have 1 over x minus c on the outside. And I'm leaving it like that for a reason that is maybe not obvious right now, but will be soon. I still have absolute values on the outside. C to x. Here, this thing is less than epsilon, which epsilon's a positive number, so this is just epsilon. dt, absolute value. But again, we're back at the situation where this is a constant, right? And this is an interval length, c to x, where now, because, so over here, I could say like, oh, rewrite it so that x is bigger than w, and then I knew that this interval was positive. Here, I don't know that x is bigger or smaller than c, because c was fixed. I didn't have control over that, right? It was some number that was given, and I've only chosen x. X is my only dummy variable within delta, so it might be bigger, right on the bigger side of c or on the smaller side of c, and I can't relabel them. I can't assume that x is bigger or smaller, which is why I need the outside interval, absolute values here. So this thing, running out of space, hopefully this is visible. I still have absolute value, 1 over x minus c. Here, I'm going to have absolute value, then I'm going to have this thing. So this is epsilon times x minus c, where epsilon is a positive number. I can pull that out, which gives me absolute value of x minus c times 1 over absolute value of x minus c. This is epsilon, which is exactly what we wanted to show, right? We've shown that this thing here, which is what we started with, is less than epsilon. And so we are done. Okay. Whew, can't believe I got that on one board. Hopefully it's perfectly legible. It gets a little intense toward the bottom there, but hopefully that was okay. All right. So again, I just want to point out that, and I believe actually in the textbook we're using as of when I'm recording this, they actually make this mistake, which is that the absolute value on the outside, they do it initially, and so they do it here, and then they get rid of it here, but you still need it there so that it will actually cancel out correctly, because you don't know whether or not x is bigger or smaller than c, so you don't actually know whether this interval, right, this integral, excuse me, is positive or negative. But nonetheless, it works. It's just you got to make sure that you keep it the whole way. And the book ended up dropping it at one point. All right, and that is that.